Today we're going to cover QuickSort, which is a sorting algorithm that is, quick. It sorts data in n log n time in the expected case, and it has a space complexity of log n. Like merge sort, QuickSort relies on the divide and conquer approach, where we sort smaller chunks of the data and then push them back together to get a final result. Inside our divide step lies something called partitioning. The key idea of QuickSort is the idea of a pivot element, which we will pick from our array. We then move all items smaller than that element to the left side and all elements that are bigger to the right side. This is what we call partitioning. Then comes the conquer step. We recursively call QuickSort for the left side of our pivot element, and then we call QuickSort for the right side of our pivot element. And by the time this is done, we have a nice sorted array. Let's do an example. Say we have the following array: 3, 4, 1, 6, and 2. Step 1 is to choose a pivot element around which we are going to partition our array. There are various methods to do this, each one more complicated than the last, but for simplicity's sake, let's choose the element at the very end of our array, in this case 2. Now, we will work from the start of the array up to our pivot element, swapping as needed to partition our array. And let's walk through how we're going to do this. First, we will set a pointer at index equals -1. This pointer marks a location where the next element that is smaller than our pivot is going to go. Then we begin iterating. Our first element, 3, is greater than 2, and we will do nothing. Our second element is 4, which is also greater than 2, so we will do nothing. Our third element, 1, is less than 2, so we will swap. But we will do this by incrementing our pointer by 1, then swapping the number at our pointer with the current number in our iteration. So 1 and 3 have swapped. Our fourth element, 6, is larger than 2, so we do nothing. At this point, we have reached our pivot element. Once we reach our pivot element, we increment our pointer by 1. We now swap our pivot element with the number our pointer is currently at. So we swap 2 and 4. Now we have a nice partitioned array where all the numbers on the left side of our pivot, 2, are smaller, and all the numbers on the right of our pivot are greater. We will now do this recursively on either side of our pivot. So on the left side we have 1. 1 is an element all by itself, so it is already sorted, and we can be done with it. On the right side we repeat the process. We will select 4 as our pivot element, and we will establish our pointer. We will iterate starting from 3 and go until we reach our pivot, 4. 3 is smaller than 4, so we will increment our pointer and swap. In this case, we are swapping 3 with itself, so nothing happens. Then we move to 6. 6 is bigger than 4, so we will do nothing. At this point, we've reached our pivot. So, to finish this level off, we will increment our pointer by 1 and swap with our pivot element. So we swap 4 with 6. We can go down recursively again on the left. 3 is an element by itself, so we are done. Then we can go recursively again on the right. 6 is an element by itself, so we are done here as well. At this point, we are done recursing down, and we can take a look at our beautiful, finished, sorted array. So to recap, step 1 is picking a pivot element. In this case, we just chose the end of our subarray, but it can get much more complicated. Step 2, we partition around that pivot element. In step 3, we recurse to the left and right side of the pivot. That is the general algorithm for QuickSort. Here's the code for the algorithm, and it is also posted as a link to GitHub in the description. I think a big part of educating yourself is taking a look at this code and working through it by yourself and not having me walk through it step by step. You already have the general idea, and here you can see how it is actually implemented. Now I want to point out something really important about this algorithm. Say we have a reverse sorted array, and we pick the last element each time as our pivot. In that case, we partition our array in such a way that it is terribly imbalanced, and we are effectively performing insertion sort on each pivot element, which is gross and inefficient. We can mitigate this risk by choosing a random element as our pivot each time. Like I said before, there are even more ways to choose a pivot that ensure we are almost splitting our array in half each time, one of which is called the median of medians, but I will save that for another video. Now let's take a moment to analyze the runtime and space complexity of QuickSort. We need to break it down into the best case, the worst case, and the average case. For the best case, we have an even split on our array, so our time function looks like this. We can apply the master theorem to this, and our runtime becomes n log n. That is the best case, and this is actually as fast as we can get with comparison-based sorting algorithms. Now let's consider the worst case. In the worst case, we pick a bad pivot, we partition the array in big O of n time, and we call quicksort on an array of n-1. The only element we have removed is our pivot, so this is not taking advantage of dividing our problem down. If we pick a bad pivot n times, and it costs big O of n time to partition the array each time, then our algorithm degrades to big O of n squared, which is gross. The good news is that the average case actually ends up being n log n. Assume that we pick a pivot that is not the worst case. Let's say we choose a pivot where 90% of the elements are on one side or the other. This means that our recursion is going to have log to the base 10 9 levels, which asymptotically speaking is equal to n log n. The space complexity is easy. We aren't creating any extra arrays and our pointers take up constant space. If we choose a bad pivot each time, however, that means that we will have a greater recursive depth on our stack, and our space on the stack will be big O of n. If we choose a good pivot each time, we are effectively splitting our array in two each time, so our space on the stack will be big O of log of n. So in the best case, it is big O log of n, and in the worst case, it is big O of n. Anyways, that is quicksort. I hope it makes sense. If you guys have any questions, please let me know in the comments down below, and have a fantastic day.